What I want to talk about today is how much can we learn in a very generic sense about biology from looking at very simple physical systems. Okay. So I want to start with the free energy principle that Carl Friston introduced in the very first talk. And I formulated it here in a way that looks as much like a tautology as possible, so that you can see just how simple this principle is. It basically says anything that persists has got to behave in a way that contributes to persistence. And if it doesn't, it stops persisting, and that's that. So I want to study the effects of this in the simplest possible physical model. And whereas Carl presented the FEP in terms of classical dynamical systems theory, I'm going to use the language of quantum information theory because it's much, much simpler. And I'm going to think about the simplest possible situation, which is some system, which I'll call S, that interacts with some environment, which I'll call E, through a boundary, which I'll call B. And this boundary is a boundary in the total joint state space. So in quantum theory, that will be a Hilbert space, but you can think of it as just the collection of all of the degrees of freedom that are of interest. And I'm going to make two simplifying assumptions. Assumption number one is that E is everything that's not S. So if I think about my interaction with my environment is just not me. So that includes everything that isn't me. And this simplifying assumption buys us something important. It means that the joint system is isolated because I built anything that we could consider to be an extra component into E. So we just have a bipartite decomposition. The other simplifying assumption I'm going to make is that everything inside is finite. What does that mean? It means that the energy flows across this boundary have to be finite. So no infinite energy flows, so no singularities and stuff like that. So I'll ask two questions. What does this tell us about the structure of S? And what does it tell us about the structure of the interaction? And I'm going to ask these questions just by looking at simple symmetries and then how they're broken. So here's symmetry number one. The FEP is a universal statement, as Friston showed in his 2019 paper, and since we've shown using the quantum theoretic formulation. And what that means, what universality means here, is just that I can exchange these labels. And I can label the left side system E and the right side system S. All that means is that because this is an isolated system, the thing I previously called S is the environment of E. And so that means the free energy principle applies to both of them. Both of these systems are acting to maintain the integrity of this boundary that separates them, because it's maintaining the integrity of the boundary that makes them persistent systems. If I take the boundary away, both systems disappear. All I have is the joint system left. So persistence requires the integrity of this boundary. And that's what the systems act to assure. So symmetry number two is conservation of information. And I can appeal from a quantum theoretic point of view to unitarity, since this is an isolated system. Unitarity is just the principle that information is conserved. But we can also think of this in terms of Newton's third law, right? Anything that S does to E, it can expect an equal and opposite response, i.e. for E to do something to S. And since these are energetically balanced, they're informationally balanced. The other perspective on this, which is very useful, is because I've required that everything inside is finite, I can use the holographic principle, which was originally developed for talking about black holes. But what it says is that the information coding capacity of any boundary is finite. And Quantitatively, it puts a number to the minimum size for encoding 1 bit, but we don't need to worry about that here. In the case of a black hole, it's 4 Planck areas, which are very small. And that defines a black hole, actually. Anything that has that encoding capacity is a black hole, and anything that has a smaller encoding density is not. But what this does, by requiring a finite information capacity, is it induces a pixelation on this boundary. So that creates a discrete topology mathematically. And it gives it a finite dimension. And we know exactly what that dimension is. It's the dimension of the interaction operator, which I've called HSE. That's just a Hamiltonian operator. And it also tells us exactly what information the boundary encodes. The eigenvalues of HSE are n-dimensional numbers, or have an n-dimensional binary representation. And so we can think of the boundary as encoding the eigenvalues of the operator that crosses it. And eigenvalues of the Hamiltonian are energy values, so any of these interaction boundaries actually encode a representation of the energy that's being exchanged across the boundary. Now this tells us something very important, which is that S can obtain exactly n bits about E, and vice versa. So the amount of information that the system can get about its environment is exactly in bits, and vice versa. So the environment can learn exactly n bits about the system. So that's a very powerful symmetry. Symmetry number 3 is a little bit more subtle, but not a whole lot. And it depends on this fact that if S and E are separable, which in quantum theory means if they're not entangled, but classically the analog is if their states are conditionally independent, which, if you recall from Carl's talk, is a requirement of the FEP, then the dimensions, which you can read just as the number of degrees of freedom, but formally it's the Hilbert space dimension, of the system and the dimension of its environment must be a lot bigger than the dimension of the boundary. Otherwise, they'll cease to be conditionally independent. Now, if that's true, we can write this operator, this Hamiltonian operator that represents the interaction in a particular really simple form, which is a bunch of thermodynamic stuff, KT and a constant, times a sum of simple operators, each of which you can think of as acting on 1 bit. There's a picture of what these M operators look like. Each one acts on 1 quantum bit that's in the boundary, and it reads 1 classical bit off of that, and then prepares that some classical bit that the system wants to prepare. So it's a very simple representation of the operator, and since this is a sum, it means that I can rearrange these M operators any way I want to. I can effectively relabel the indices any way I want to. And what that does is just swap what 1s and 0s are written in what positions on the boundary. And since the boundary encodes an eigenvalue of energy, when I move 1s and 0s around, I change the eigenvalue. So I change the value of the energy that's coming across the boundary from the perspective of the system. All that means is that I'm moving the 0 point of energy up and down. And I can move that point up and down arbitrarily without changing anything about the physics. So this exchange symmetry doesn't do anything to the interaction. It just changes the numerical value that's associated with it on one side of the boundary. And this is actually required for separability. If I lose this ability to freely choose what basis I'm operating in, so how I've labeled the boundary with bits, then it turns out that induces entanglement, or that's just a way of defining entanglement. So I have to have this free choice of moving things around. Okay, so those are three simple symmetries of any generic physical interaction between finite systems given this condition of separability, in other words, conditional independence of their states. So now we can start talking about biology and what we can learn from this. And the bottom line is that any system that's actually interesting breaks this third symmetry. And what I'll spend the rest of the talk doing is looking at ways this third symmetry is broken and how they give us bits of information that's interesting from a biological point of view. So if you don't break this third symmetry, you just have a quantum noise interaction. Right? There's nothing outside the system to contribute any classical perturbation. So there's no classical noise at all in this picture. So this thermodynamic interaction is just quantum noise. But any system that acts irreversibly on its environment, so it does something to its environment that affects what its environment is going to do to it, that is what I mean by irreversible here, has to burn some free energy to do so. And the reason is just Landauer's principle, that if I write a bit irreversibly, that costs energy. I can read bits all I want, as a previous talk pointed out, actually. But writing bits costs energy, and that energy can only come from one place. It can only come from the environment, because I'm working in a closed joint system. So if S is going to get extra free energy, it has to get it from E. So this breaks the symmetry of the interaction if I'm doing anything irreversible, because I have to say, okay, I'm going to dedicate that bit of the boundary to a free energy supply. And we've all got perfect examples of that. The power cord in your computer is a thermodynamic sector of its boundary. And you don't do any information processing with that free energy that comes in. It powers the information processing that you do by typing on the keyboard and playing with the mouse and all of that. Your food supply is an example of a thermodynamic sector of your boundary. So this is the first symmetry breaking that actually characterizes life. It's got to get free energy from someplace so that it can act on its environment in a way that actually influences its environment. And if you recall from Carl's presentation, that action on the environment is half of the active inference equation. Learning is the other half. So now let's think about memory. If I want to act on my environment and I want to store some observed consequence of my action, then I've got to write a bit someplace. And since I'm working in a quantum theoretic setting, the only place I can put classical information is on the boundary. Now, maybe I'm taking that boundary and pulling some of it inside me. And I'll show you a picture of that a little bit later on. But wherever that bit of boundary is, I've got to write this classical information on the boundary. So I have to break the symmetry again by allocating some sector of the boundary to the memory that I write. And that does an interesting thing to the inside of the system. It says that the inside of the system has got to implement a clock, a simple clock that counts bits, because it has to be able to distinguish information from then from information from now. And that requires a time variable. So it has to implement this little internal clock. And this clock turns out to be what in the theory is called a quantum reference frame. It's a physical object that encodes some standard which is internal to the system and specific to the system for time.